So we're talking about density, specifically the density of water. Just to remind you, as I'm sure you've heard in every science class you've had, density is equal to mass per unit volume. Mass for water we're going to be talking about is grams, and volume can either be centimeters cubed or milliliters. They're exactly equal, which gives us a density for pure water of 1.0 grams per centimeter cubed or 1.0 grams per milliliter. Now, density is affected by lots of things, but for water, the three main things it's affected by are temperature, pressure, and salinity. And when it comes to the relationship between temperature and density, for most substances, as temperature increases, meaning it gets warmer, density decreases. This is an inverse relationship. For water, that's not completely true all the time. In a general sort of way, as temperature goes down, density goes up, but it doesn't continue that way forever. We know that ice eventually floats. And then the other relationships between density and pressure. The more pressure you apply to water, the denser it gets. So that's a direct relationship. As you increase salinity, you're adding more weight per unit volume, so you're also increasing the density. So both of those are a direct relationship. Now, let's talk about the relationship between density and temperature real quick. As water cools from whatever temperature it's at downwards towards 4 degrees Celsius, the density does increase, as you would expect. And this number ends up being kind of important. So make sure you know this number. It's called the maximum density of fresh water. What happens at 4 degrees is we've removed enough energy that the molecules are moving slower and slower. And you can see that in this picture. We're looking at figure 5.1 in your book. 5.10, excuse me. So we're cooling down the particles. They're moving less and less, and they begin to make more and more hydrogen bonds. Remember that the bond angle of water is about 105 degrees, 5 degrees. What that means is that in order to make the hydrogen bonds, we begin to make that crystal lattice structure. And that maximizes, that begins to form at 4 degrees Celsius and below. And as water begins to freeze, it adds more and more molecules to that crystal lattice structure, actually decreasing its density. So if you were to actually look at the density of water as a graph, and I'm going to draw kind of right on top of this. Let's say you have temp down here and density over here. I'll just put it as a D. And generally, as temperature decreases, we will have the temperature decreasing. The density goes up. But at the magic point, which is 4 degrees Celsius, it begins to come back down until we get to ice, and when it has expanded by almost 10%, around 9%. So once we're done with density, we need to talk about salinity. Salinity is going to be the next few slides. Salinity we've talked about already in marine chemistry, but we just sort of only ever talked about salt. But salinity actually includes other things. It actually includes dissolved gases. Includes. It excludes a bunch of other things. It excludes dissolved organics, basically fish poo. It excludes any sediment that's stuck in it. And it's excluding any solid materials that are just in contact with the water. That one kind of makes sense. So it's a total amount of dissolved solids and dissolved gases. Those two things together. Now, the definition of salinity is right here. Ratio. You need to know this. The ratio of mass of dissolved substances to mass of fresh water sample. That's a definition of salinity. And seawater can be expressed as percent or parts per 100, 3.5. If we're going to do that more typically, we would call it 35 parts per 1,000, which is kind of what you guys are used to hearing more, but it's still 3.5%. And it is much saltier than fresh water. But because it's still mostly fresh water, the vast majority of properties are the same. Not all of them, but most of them. And we'll talk about that more as we go on. You've seen this graph before. I know you saw it in Chem. 99% of all the dissolved solids are mostly chloride at about 55%. then sodium, sulfate, magnesium, calcium, potassium. You need to know these 6. These are the 6 major constituents of salinity, and you need to know them in order. If you look at this little tiny piece of the pie, right there, which is basically a little less than 1% of the volume of solids that are in seawater, it actually makes up almost all known naturally occurring compounds. Naturally occurring elements. There's even gold and platinum in seawater. Again, it's typically expressed, the preferred one we use, or the one you'll see most often, is this one. These are all equivalent, though, and salinity is a major constituent because it's given in parts per thousand. We will talk about some of the minor constituents and mention, if you look over the book in this section, trace constituents, which are each of these mean parts per, M means million, B means billion, and they're very, very uncommon. But some of the things we're concerned about, like mercury, methyl mercury, it's a pollutant and it's actually a trace constituent. Even in those small amounts, it can be really dangerous. Also, remember, we include dissolved gases. So the gases carbon dioxide, nitrogen, and oxygen are all found as part of seawater. If you remember, oxygen is about around here, 8 parts per million, making it a minor constituent and thus a minor gas. CO2 is also fairly common. Nitrogen is probably the most commonly found dissolved gases. And then there are other minor nutrients. You'll notice that some of these are very, very important. Even silicon. These ones are all important biologically for life. You've heard of nitrogen and phosphorus when we've talked about eutrophication in the past. Silicon is used by a lot of organisms to make their shells, like diatoms. And then iron is very, very important when we're talking about the iron hypothesis, which we will talk about later on in this course. So determining salinity. The earliest method was evaporation, which was basically they just boiled water till all the salinity was gone. There were some problems with it. First, you never knew when it was really dry. You also lost some of the substances. When you evaporate water, you lose the dissolved gases. It wasn't particularly accurate. It didn't make that big a difference, but some. And any sediments that are floating around would also, and organic, the fish poo, the marine snow, would still be left behind and included in your salt calculation. The law of constant proportion is really important, and I don't make you learn too many guys, but this guy's important. His name's William Dittmar, and he came up with the law of constant proportion. He was actually the chemist aboard the HMS Challenger, and he was one of the guys who went around and took those hundreds and hundreds of samples of seawater they actually still have all over the place. And what he found is that whether your salinity was 1% salt or 100 parts per thousand salt, once you dried it, the salt all had the same proportion. There was always it was always 55% chlorine to 23% sodium, and so on and so forth. And always in the same order, regardless of whether you were in the Mediterranean, which is incredibly salty, or in your brackish lake. And this came to be known as the law of constant proportions. What this means is that the way we actually measure salinity is we don't measure salt at all. We actually measure chlorine. It's much easier to measure the negative ion. It's kind of complicated chemically. But basically, whatever your chlorinity is, you multiply it by 1.80655, and that will give you salinity. You guys know I love math, so we will be doing some of these soon, so make sure you have that formula. The salinometer, I don't think we've actually used this term with you much here at MAST, but it's actually part of a CTD. And it's a conductivity meter is another name for it. And basically the way that it works is fresh water doesn't conduct electricity particularly well. This is supposed to be showing that, there's a current going from one to the other. And if there's a current, it lights up a bulb. Nope, I think I drew that the wrong way. We'll put the arrow there. When you have salt in the water, there's electrolytes, and those carry charge pretty well. And the more you have them, the faster it carries a charge, and the stronger it carries the charge you put into the water. It's basically how a conductivity meter or a salinometer works. Now, parts per thousand, right here, I use all the time, and you really should correct me. What we want to use is the PSU. The PSU is the practical salinity unit. They kind of got rid of PPT because it makes it sound like we're directly measuring salinity, and we're only directly measuring chlorinity, or the chlorine ions that carry the charge. So it's more scientifically correct to say practical salinity unit, or PSUs. Luckily, they're exactly 1-to-1. Interestingly, if you calibrate well, you can actually get to be as precise as 1/1000th of a parts per thousand. It's incredibly accurate. So the problem is, how often is it calibrated? I know our CTDs, the YSIs we use, only get calibrated once a year, which is probably not enough for very precise measurements, but it's good enough for the research projects we do. IFR is another method, and it's one you've also used. It's basically index of refraction, and you've done this whenever you used a refractometer. Basically, the idea is that the speed of light is different depending on how many salt particles there are. It's not always as accurate. It's also a function of temperature, and you need pressure to be constant. But we still use them, and the reason we use them is because they are cheap, and they're fairly easy to use, and if you break them, we're not as concerned. Another method that we rarely use here at MAST, and some places still use it, is the hydrometer. We actually measure the density of the water. We know that the two major effects on density are temperature and salinity. So if you know density and temperature, you can backtrack to salinity. So basically, you read this hydrometer. I can show you one tomorrow in the lab. It looks sort of like a thermometer with a weirdly bulbous end. It can be very, very accurate, especially if you know temperature and if you're at sea level. The farther you get above sea level, or I suppose below, it becomes less accurate because pressure becomes an issue. It's cheap. They don't work well on a boat. You can see that you have to look at the meniscus here, and the problem is if you're on a boat, the meniscus is going to be sloshing back and forth. So the hydrometer is a method that's still used occasionally in labs. It's frequently used to test if a CTD or a salinometer is still precise, if it needs to be calibrated, but we don't really use it in the field at all. We're actually going to stop there. That's going to be the last part of this section, and we'll start up with some of the issues related to salinity on the next one.